Okay, hi everybody. We are going to be taking notes on graphs of exponential functions, and you're going to put that on page 127 on your table of contents. The homework that we're going to do that's related to this lesson is out of your textbook, and it is section 3.1, numbers 1 through 12 and 15 through 19. The focus of this talk is going to be on how you create graphs of exponential functions and the properties of the basic exponential function paragraph. All right, let's get started. You should have already received this handout. Let's go ahead and put our page number on top of it. So it's page 127 in your notebook. Today's date should be the 12th, if you're doing this on Thursday. And these are notes. Okay, so you can see that a basic exponential function has the form y equals b to the x, where b is greater than 0 and b does not equal 1. The reason why b does not equal 1 is if we had 1 for the base, when we plugged a number in for x, we would just always get y equals 1, and that would be a horizontal function. The reason why we want to have b be greater than 0, which means it's positive, is if b were a negative number and x was, say, something to the 1/2 power, then we would have an imaginary number because we'd have a negative underneath the square root. So we'll always have positive bases, except the base cannot be equal to the number 1. All right, so to construct a graph of any basic exponential function, we need to make a quick table of values. So let's go ahead and make a table of values from -3 to 3 for the exponential function y equals 2 to the x. So I'm going to plug -3 in for the exponent. So we'll get 2 to the -3. Using our properties of exponents, that's going to be 1/8. We'll have 2 to the -2. So that's 1/4. And we'll have 1/2 for the next one. Anything to the 0 power is 1. 2 to the 1 is 2. 2 squared, 4. 2 cubed is 8. So now I'm going to plot these ordered pairs over here to construct the graph of the function y equals 2 to the x. So when you go to -3, 1/8, that's going to be really close to the horizontal axis. -2 will be at about 1/4, then 1/2, then 1, 2, 4, and 8. One of the things to notice as you're graphing this is each time we go over 1, we're doubling the y value. So this is getting that exponential growth curve going that you studied last year in Algebra 2. Okay, excellent. Now let's go ahead and graph a related function. Let's go ahead and graph 1/2 to the x. It says here on the directions that you can use your calculator to help you fill out the table, but I think if we think about this a little bit, we might be able to use the numbers in the previous table to help us complete this one. So if we take 1/2 to the -3, I know that's going to be the same as 2 to the -1 to the -3, and that's 2 cubed, which is 8. Now, I'm not going to go through this whole long process in every one of these. I think you can see if we took 1/2 to the -2, everything would be the same that I did here, except this exponent would be -2, which would make this exponent be +2, and 2 squared is 4. And so we're going to take these numbers up here, and we're basically reversing their order when I have the reciprocal of that base. So the next number is going to be 2. Anything to the 0 power is 1. And now we'll have 1/2 to the 1, which is 1/2. We'll have 1/2 squared, which is 1/4. And up here we'll have 1/2 to the 3rd, and that's 1/8. So when you go to sketch this one, graphing these ordered pairs, -3, 8, 2, 4, 6, 8, and -2, 4, 2, 4, -1, 2, 0, 1, and then we got to squeeze in 1/2, 1/4, and 1/8. We can see that we've got a graph that is actually a transformation of the one above. So the graph of y equals 1/2 to the x is a reflection of the graph of y equals 2 to the x about the y-axis. We can actually prove that that's true if we think about rewriting 1/2 to the x as 2 to the negative 1 to the x, which is 2 to the negative x. And now if you recall, when we had a negative on the inside of a function when we were doing transformations earlier, that represented a reflection across the vertical axis. So we take this function, reflect it across the vertical axis, and we will have this function as the result. Let's go on to the next page. When you attach these pages in your notebook, make sure that you set it up so that you can flap the pages open. Okay, so take a few seconds. We're going to pause the recording, and I would like you to work on this with a partner. So we're going to state the domain and range of the exponential function of the form y equals b to the x. We want to generalize it now from our examples with 2 to the x and 1/2 to the x. So go ahead and pause the recording, and we'll come back in just a second. Okay, great. Good work on this. Let's see what you got for your answers. The domain of these functions is all real numbers. And the range of the function is all of the positive numbers. So our y values have to be greater than or equal to 0. All right, now if you paid attention on the last page, we can determine really quickly whether or not an exponential function is increasing by examining the value of b. So if we look at the base, and the base is greater than 1, the graph will be increasing. And if the base is between 0 and 1, remember it can't be negative, the graph will be decreasing. So I can see that this function has a base that's less than 1. This function has a base that's less than 1. This function has a base that's greater than 1. This function has a base that's less than 1. So the function that will be increasing is y equals 5/4 to the x. All right, the next exercise we have to do is to determine the y-intercept of a function and then explain whether or not it increases or decreases. So this one is slightly different. It's been stretched by a factor of 7. So if we go in now and take a look at the y-intercept, we always are going to find the y-intercept the same way. We want to evaluate the function when x is 0. So 7 times 3 to the 0 is 7 times 1, which is 7. So if we have an exponential function of the form y equals a times b to the x, I know that a is going to be the y-intercept. I also know that this exponential function is increasing, and it is increasing because, the base is greater than 1. Let's make a sketch and label the y-intercept. So we can just plot a few points. So I know that my y-intercept is going to be at 0, 7. If I plug in 1 for x, up here, we're going to get 21. And if I plug in negative 1 for x, we're going to get 7/3. Now 7/3 is 2 and 1/3. So, maybe down here somewhere, real roughly. And all exponential functions kind of behave the same way. So when you go to sketch your graph in, we don't need to have it be too elaborate. Okay, so let's take a look at functions that are transformations. I can see that this function is a transformation of this function. We're adding 4 to the function. So this is going to shift the graph, or translate it, vertically by 4 units. All right, so if we want to determine the y-intercept of this function, again, we're going to let y equal 0, or x equal 0, excuse me. and anything to the 0 power is 1, so that's going to be at 5. Now, here's the deal though. If we are translating this graph vertically by 4 units, then we're also going to be translating the horizontal asymptote vertically 4 units. So I'm going to translate my horizontal axis up 4 units as I get ready to sketch the graph of this function. I can see that the base is 1/3, so this is going to be a decreasing function. And if I wanted to, we could plug in 1, and we'd get 4 and 1/3. And if I wanted to plug in -1, we would get 3 here, because 1/3 to the -1 is 3. Plus 4 is 7. So if we want to plot just a few more points, here we're going to be something like this. And most importantly, though, we want to get that horizontal asymptote in at y equals 4. So maybe we'll label a couple more points here. So this will be 1 and 4 and 1/3, and this point here would be -1 and 7. Okay? All right, so you're going to be doing some graphing in your homework. Some of it is going to involve transformations, and you're going to be asked to compare how a function's graph compares to a basic parent graph. And the 2 main types of transformations will be transformations that involve scaling the graph by a scaling factor, so a vertical stretch or compression, and then either a translation horizontally or vertically. And don't forget, we also did one over here where we talked about the graphs as a reflection of the graph. So if you see a negative exponent like this, you know that the graph is going to be a transformation of whatever the graph space is. All right, have fun on your homework on this and do some good sketching.
All right.